I hope. Hopefully you never feel bad about asking questions in here. Ooh, got myself in the face. I do want to take a quick trip backwards momentarily before going forwards again. I have to find the spreadsheet too. Is it here? I think it's here. It's here. All right. Yeah, that's good. I want to show you a little something I built. You can let me know if you think it's useful or not. It's not the best coloring, I apologize. I've been told by many people that I pick awful colors for my spreadsheets, including the entire negotiations team for COCC. And I say, well, focus on the data inside. They're like, I can't even see the data because it's all McDonald's colors. Whatever. So anyway, let me explain what you're looking at here, because there is quite a bit going on. And you have to realize that the mathematics behind this is going to apply in general for all data sets. If you don't believe me, yay, that's awesome. That's why I proved it for you on the enrichment page of your website. I've got mathematical proofs of everything I'm about to say to you guys, if you're interested. Or if you have trouble falling asleep one night, you can read that. So what I've done is here, I've made up a population of 6 values. Boop, 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 boop. And I set it up so that I can randomize those 6. If I press F9, I get new population values each time. And all they are, if you look at the command in there, it's a random number command. It takes a random number, rounds it off to 2 decimal places, and drops it into that spot. So if you had me in 243, I'm sure you're sick to your stomach of doing randomizations because it's what we did quite a bit back in that class. Okay? And here are the population parameters of that population. Population average, the population median, the population standard deviation, remember that guy, little sigma? We didn't talk about him much in 243 until the very end when we talked about probability distributions because we actually had the entire population there in front of us. Population, remember what it's called when you square the standard deviation? Do you remember that? It's okay if you don't. We mentioned it maybe twice. It starts with a V. It's the variance. Yeah, it's the variance. I only bring it up here for maybe 5 minutes. So if you don't be like scared. We mentioned it with Bert and Ernie when we calculated out the standard deviation. And then I said, just here, this is it, and then we can just forget about it for now. And then we'll go back to it, 244. Here we are. This is a simple little measure. What proportion of the data is greater than a half? So if you look up at the data up there and look at the numbers, kill the lights a little bit so you can, is that a little bit better? Maybe-ish. If you look at that data point, 0.62, 0.52, 0.91, and 0.88. 4 of the 6 data points are bigger than a half, so it's 0.67 or 2/3. What's the average deviation? This is one of the, I included this because my 243s always invent this every term. I love it. It's another measure of variation sometimes used. I look at the mode, sometimes there isn't one, like right now. The range, which is the high minus the low, and the skew. Remember what skew is? What is data when it's skewed? Or what is data when it's not skewed? Elizabeth, go!
There's more to one side than the other.
I love that. Asymmetrical leans a little bit. And it's kind of hard to see a lean when you only have 6 data points. But there is a mathematical formula for it that you may or may not have learned in 243. 9 population parameters, all of which can be used in one form or another to describe a population of numbers. What's the problem with describing a population of numbers? What's the problem? You don't know the population mostly, right? So here's one where I'm creating a bit of a fiction because I'm telling you here's the population of numbers. So it's fictitious in that respect, right? It's fictitious because I'm telling you that's the population. Realize everything we're about to discuss will apply even if this population were so big that we couldn't see it all, and even if the population were so big that we didn't know these values right here. Because we wouldn't know those values in the general population, would we? They'd be hidden somewhere else. Now what I want you to do is realize I've got these 9 values on each of these 9 line charts over here. You can find them. If you look at the green triangles, they are graphed over here. Like right now, which one's this? This is the average, 0.51. There he is right there. From 0 to 1, he's at 0.51. The median's at 0.57. That's that guy right there. Can you see the number lines underneath from 0 to 1? The sigma's 0.35. Where's sigma? They're right here. Right there, 0.35. There's no mode. I don't know why I put them in that order. That's kind of strange. Sigma squared, that's the variance. He's over there in yellow. That's the 0.12 up there. And so forth and so on. So each of the parameters is graphed on a number line. In reality, could we do that? Could we graph the parameters on a number line in reality? In reality, of course not. Of course not, right? Because you wouldn't know what they were. They're out there. The population has them. but you don't know what they are. So what do? You take a sample. You take a sample. Now, what I have on this top line with the blue squares, or blue diamonds, whatever they are, is every possible sample of size 3 drawn from this population. Every single sample of size 3 drawn from the population. Used Excel to do it, thank God. It took a while to set it up, but we got it done. So there's quite a few averages, a few medians, not so many modes, quite a bit of variance, quite a bit of standard deviation, and I plotted them all on the top of that. So you see some of them are very, very far away from the parameter values, aren't they? For example, if the average is a 0.51, this one here has an average of just over 0. I'm guessing what happened there was all the small values were sampled, the 0.02s and the 0.09s. And it's possible that if you go into that population of size 6, and grab 3 values, you could grab the 0.02 and the 0.09. This is also sampling with replacement, not without. So you could pick the same value more than once. Just like what could happen in a Gallup poll. That could happen if Gallup surveys 1,000 Americans. So everybody okay with that, with the blue, which shows up the blue? And notice it changes. They'll change too as the population values change. You see all these green things floating right here, these little green flags? Those are all the samples hidden in white text behind. So every time I press F9, I tend to make Excel work out. Usually these things happen instantaneously. It takes about a half a second. So Excel's working its butt off right now to do all this. Now, what does the red square indicate? What does the red square indicate?
The average of the samples.
The average of the samples statistics. So this red square here is the average of all the sample averages. This red square here is the average of all the sample medians. This red square here is the average of all the sample modes. Some of you might be wondering, wait a minute, why the hell is this one here? Shouldn't it be more centered? You got to realize that Excel does a terrible job at this. There are sometimes blue squares on top of blue squares. So there might be more than one blue square right there. There might be a stack of 5 or 6 of them, but you can't see that. It's unfortunate. I wish Excel had like a third dimension that would come out at you, but I can wish all I want. Average of all the skews, average of all the little sigmas, average of all the little sigma squares, average of all the average deviations, that's kind of a fun thing to say, average of all the proportions, and average of all the ranges. Okay? It's a lot to look at. We're almost done too, I apologize. We're almost done. I colored 3 of them yellow. 3 of the average, the variance, and the proportion I colored yellow. I'm going to press F9 a few times. I want you to tell me why. I want you to tell me why I colored those 3 things yellow. I think this is badass. I appreciate that. I think it's badass too. This is about 4 or 5 hours to put this thing together, yeah. Totally worth it. I think it's totally worth it. I gotta hide those green flags. The green flags piss me off. They're error flags. It's asking me if I'm sure about that calculation. I don't want to tell it yes like 500 times. There's gotta be some mass way of doing it. I just haven't figured it out yet. Can anybody see why I made 3 of them yellow and the rest are just not yellowed? Let me see hands on this if you see it, if you see it. Jim, go! Paul.
The average of samples and parameters stay the same.
The average of the samples, that red square, is always the same as the parameter value. That you don't know. So, for example, the average of the sample averages right now is exactly equal to the parameter value. Now the parameter is 0.58, but you won't know that because that's a parameter value. So why am I excited about the average of the samples equaling that? Why am I excited? What do you want to know in your population? What would you like to know about your population? For example, you're making a drug that fights headaches. What would you like to know?
That it works.
That it works. That it actually decreases the incidence of headaches, or that it actually lessens the time you have your headache. So you want to know the average length of time, or the proportion of people that are helped by that headache medicine, right? Are you ever going to know it? In the population? That's the problem. You're never going to know this. Can you know this? Ha! So, sorry, that was a little bit louder. Since you can know this, you get this for free. You see
Is it
my...
always the same?
Yes, for this, and that. Now, mathematically, if you don't like Excel, if this isn't proof enough for you, as well it shouldn't, because this is not proof. This is just demonstration. I put the proofs of all three of these things on the enrichment page of your website. They're called unbiased estimators. Unbiased estimate. I have a quick little PowerPoint to walk us through this, and I want to just leave it at the break and keep going. But let me get in here and show you this right quick. We'll come back to that. We did all this already. Yeah, I brought punk rock into today. Yep, I even got punk rock involved. Where is it? 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 We went through all this already. Maybe it's not this one. Oh, yes it is. Okay. Here it is. So, the reason I had those three in yellow, and again, this spreadsheet is already linked from last week. So these slides are available. You might not have gotten a chance to look at them yet. That's totally fine. The three statistics, the sample average, the sample proportion, p hat, and the sample variance, little s squared, are called unbiased estimators of their population parameters. Because on average, their average values hit the parameter values. So you got to remember, what you're trying to do is identify what the parameter values are. You want that, right? That's the whole point of doing statistics, is you want to know that parameter value. The catch-22 is you can't know the parameter value. The catch-21, if there is such a thing, is that this gives you like a wormhole. You can look at this, which is reflecting that. So although you can't see that directly, you can see a reflection of it in its sample statistic. There are only these three. All those other statistics, the median, the mode, the range, anything else, even the standard deviation itself doesn't do an unbiased job. Did you catch how the square and the triangle were off and the rest of them? Sometimes they got close, but on average they weren't exactly the same mathematically. That is the important part. Now, here's the catch. Here's the catch. And like I said, you guys are going to have this. This is already linked for you on your schedule page. It's yours. Merry Christmas. Do with it as you will. Because we don't have enough time, I'm going to ignore the sample variance in this class and focus exclusively on the average and the proportion. I don't like taking the 10 weeks we have and spreading it too thin by bringing in the variance. So we're only going to focus on the average and the proportion. Average and proportion. For two reasons. Number one is the time reason. Number two, I've never seen a study yet that analyzes variances. Yet. I've been digesting statistics for almost 20 years. I have not seen one. I see these almost every day of my life. So it's kind of like, why focus on the edge of the coin if you're flipping it, if you're only getting heads and tails? That's kind of that to me. So we're going to go ahead and ignore that. And it's not even in the outcomes for your course anyway, so yay, we're not cheating out of anything. Now here is a problem. This is a problem. I think you knew this already. Chris, you mentioned it almost immediately on the first couple days of class. Here's a screenshot taken from that Excel sheet. So there's the parameter value you're trying to estimate. And this is the sample average. The average of the averages. So yeah, the average of all of these comes out to be exactly equal to the parameter you're estimating. But here's the problem. If you do a statistical study, your results, where do your results lie on this graph? Which one? That's a bit of a loaded question, isn't it? That's a bit of who told me sample? Brian, yes. So you're going to be up here, right? Yeah, this is where you're going to be. Where? This one? That one? That one? Anywhere. Any one of those is going to be your result, isn't it? Right. Any one of those is going to be, you don't get this unless you somehow exhaust every possible sample from the population. Well, if you could exhaust every single possible sample from the population, go home, put your feet up, get a glass of wine. Because if you could do that, you know your population, and you don't need Matthew 44. You'd also be Yoda by the time you were done. I mean, that's ridiculous. You can't do that, right? You can't do that. So you get one of these. Well, that's a problem now, isn't it? Because if you extend this up, do any of the samples exactly hit the parameter? No, their average does, but the individual samples don't. What do we call that? Sampling error. We've been talking about this since Matthew 43. We've talked about it a lot the past couple days. How do we fix it? Thank you, ladies. We slap a margin of error. And even if you're greatly offset from the parameter, By putting the margin of error onto your sample, you increase the chance you've actually trapped the parameter value. This is why it's so crucial to include the margin of error. Because if you look back at the last slide, none of the actual averages hit. But if you slap margins of error on them, almost every single one would. Now, if you get to the extreme value out here, you're going to miss it, aren't you? But that's why we call the confidence what? 95%. It's not 100%, right? It's 95%, it's 99%, whatever it is. Some of them are going to miss. I have a whole quiz. It's coming. I think next week after. I got a beautiful quiz based on Excel for you guys to learn what 95% means. I've had students get pissed off. I only got 75%. Yes, but like 5 of your neighbors got 100, so it averages to 95. That sucks! No, that's math. It's math. It's just the way math works. It clumps, right? 105, it clumps. Sometimes it clumps in a bad place. Fair? That's the idea. That is the idea of why we're sitting here today, tomorrow, for the next 7 or 8 weeks together. My God, the term is a quarter over after today. That's kind of terrifying to think about. Yes. You already know more than most Americans do. That's pretty badass. Now you know it in conversation. Now we're learning the mechanics of why everything works. But right now, immediately, you look like you need a break. So let's take our, yes, I was like, yes, let's take 5. Stop yelling at me, Sean. You can tell you're excited. I'm not quite as excited. Let's take 5, get some air, get some water.